video, we will discuss how normal curves can be compared to each other with the standard normal curve. Remember that a normal curve approximates a set of data from a histogram and is used to calculate probabilities. The standard normal curve is the curve where the mean is 0 and the standard deviation is 1. Mathematicians have also made it so that the area below the curve is equal to 1. Let's look at an example of a normal curve that represents the amount of seltzer water there is in a typical can of Polar Seltzer. This is a soda that's in the US. The can says that there are 12 fluid ounces of water in the can, but the reality is that there might be some wiggle room for how much there actually is in the can based on some small error in the filling of the cans in the factory. A group of data scientists collect data on how much seltzer there actually is in the can. They come up with a histogram that can be approximated by a normal curve, as seen in this diagram. The mean is 12 and the standard deviation is 0.1. So the normal curve would look like this. Now suppose that the Polar Company wants to compare their accuracy for filling a 2-liter bottle of seltzer with the cans. One is measured in liters and the other is in fluid ounces. How can you compare? First, let's look at a normal curve for the liter bottle. It has a mean of 2. And a standard deviation of 0.1. I'm just going to keep it the same for ease. I move it down, there we go. In order to be able to compare this with the one we just saw that has a mean of 12, we have to find a way to look at the graphs in a similar way. This is where the standard normal curve comes into play. If we want to compare data that has different means and standard deviations, and even different units, we can use what's called a z-score. A score is a value that standardizes or makes standard any value with any units so that they can be compared to each other. We do this by subtracting the original mean from the data point we're looking at and then divide by the standard deviation. We subtract the mean to find the value that describes how far it is from the mean in the units that we're talking about. And then dividing by the standard deviation allows us to get a unit that is based on the original standard deviation. So for example, it says z equals x minus mu. So that's the data point minus the standard deviation. And then we divide by the standard deviation. Sorry, data point minus the mean. So if we actually take the mean and try to standardize it, what should we get? Well, if you use the formula, you should get 0 because the mean in the standard deviation curve is 0. So you want the mean of the data points that you have to correlate or be standardized to 0. So let's just try it. If 2 is the data point, but 2 is also the mean, doesn't even matter what the standard deviation is, you're going to get 0. So the standardization of the mean of any data is going to be 0. And that's one reason why we want it to be standardized, because now we can compare them to each other. Now let's look at how this is used. Suppose we want to compare a can of seltzer that has over 12.05 fluid ounces to its counterpart in the 2-liter bottle. One way to look at this is to find the value for which the 2-liter bottle is just as far off from the mean. So we first need to standardize 12.05 fluid ounces. I set the standard deviation for each of these variables to 0.1 just for this example. So to standardize 12.05, we subtract 12 and divide by 0.1. So this is the z-score for 12.05 on the original cans of seltzer. If you look at the standard normal curve, where is the z-score? 0.5. It's above the mean, a half a standard deviation. Where is 12.05 on its normal curve? It's above the mean and something that is comparable to the value above the mean that the 2 was. Basically, they refer to the same position on the normal curve. So now the question is, what value of liters is describing the same amount of error from the mean? We need to rearrange the equation in order to solve for the data point instead of the z-score. So we would say sigma times the z-score is equal to x minus mu. And remember, the x is the data point we're trying to find. So sigma times the z-score, oops, let me erase that, plus mu equals the data point that we're looking for the values, right? So in this case, I have my sigma, which is 0.1, times the z-score, 0.5, plus the mu, which equals x. So this is 0.05 plus the mean equals 2.05. The value x would be equal to sigma times the z-score, 0.5, plus 2. The value of the amount of liquid in the 2-liter bottle is as bad, so 2.05, which is like here somewhere, as the amount of 12.05 fluid ounces in the can. The 0.5 that is the same is only in this example because both of them have the same standard deviation. That isn't always going to happen. That is 0.05.